Yeah, because you're gonna. Don't you guys know this? Are you not aware of this thing? Because today is gonna be the summit of this class. So from this on, your life is gonna be downhill. Seriously, I'm not joking. What's that? Yeah, I'm gonna celebrate the success of your life. Your life, not my life. Yours. Yeah. So that's a reason. Do we need? Do we need this other? Oh yeah. Yeah, we have a plenty of time, and it's already online. Everything looks pretty good. Okay, I see. I see. The one thing that I need to test is like which one of these, because one pen is out of the battery, and I need to put this one too. Yeah, but let me take myself to OBS. It looks really amazing already. So the top part should be cropped a bit. Oh, where is the camera? This one. No, where is the camera? Video capture device. Oh yeah, I need to unlock it. Should I crop this a bit? What was that? Was it dwarf? Alt. Like this. No, I'm gonna stand. So it's gonna be like this, but it's gonna be not cutting my head. No, no, it's perfect. It looks perfect. One more thing is that this guy, this projector, but I think it is on already. Uh, says what? You wish that? Ah, that would be fantastic. That would be really, really good. So then it will be just my head flying around. Yeah, this is something that we can propose to university administration that they need to get these, you know, green overalls and the green screen. That would be fantastic. So it's only the head that is floating. Hands, yeah, green overalls. That would be something. Yeah, but even this is what we need to set up every single time. That green screen, even the green screens are missing in each of the lecture rooms. I don't understand why. Because others they're doing their streaming as well. But yeah, okay. So let me see where I am here. So this. Oh, this is a really good. That's really good. Yeah, the camera that is following me. Yeah, that's. Yeah, oh yeah, this yeah. This one is. Oh yeah, the cable is not connected. That's why. Okay, so let's see how we look in OBS. This looks good. YouTube. Okay, I got the message from my YouTube channel that I'm live. So let's take a look. Looks good to me. So can you check how is my voice? Because headset is different than usually. How is it? Everything is perfect. How is my voice? So it's not the ultra low latency. Is it the voice coming out? Yeah, I think it is okay. Sounds good. Sounds good. So in 5 minutes we're gonna go. What's wrong? That it was? Really? Really? But okay, so let me see what I can do for that. Is it like too, so it's not loud enough, or what's the big problem? Or it's just the quality is not great? Volume. Okay, so I increase the volume. Is it any better? So it's a max volume at the moment. But it seems that it's some voice is coming out even when I'm not saying anything at all. Is it? So a little bit like white noise, background noise. Yeah, so probably that's the reason. I don't understand like why the headset was not working well, even though that is almost like brand new headset. When was it? Was it on Friday when it was raining like hell? Yeah, so my computer would got all wet. Even the water came off from this USB-C connection. It was like I was so sure that he's not gonna able to recover from that, and it recovered. Yeah, yeah. Okay, so we're good. So I'm gonna just take this connection like this. Very good. 3 minutes, then we're gonna go. I don't get it. Like I think the whole building number 6 is falling apart because it's a, the electricity was off. The elevator is most of the days is not working. I don't get this thing. So weird. Is it, yeah, dramatically. Yeah. Okay, 2 more minutes and then we're gonna go. Okay. How can I put this again? This thumb up like or that I like this channel so much. How can I do this here? Can I close this one? Oh yeah, yeah. Thumb up. Okay, so it's two thumbs. So it was somebody else in addition to me. So it's not just me. Two thumbs. Yeah, it was you and me. Okay, so we both think that this class is fantastic. Best ever. Yeah, this is, I think this may be a little bit biased voting, but what are you gonna do? Oh, there's another
You know,
voting,
you
so
can
I,
say that okay, it reaches 100, you're gonna give the like I don't know.
100 thumbs up. Yeah, that would be, so if there are 100 thumbs up, then I want additional points for sure
Yeah,
for each of the participants. Yeah, definitely. The entire class will get the 100, I mean, one extra point,
one extra point.
one extra point. Okay, I guess we're gonna get started momentarily. I look at that, the thumbs, the number is increasing. I
Yeah.
said already like 6, 7, 7, so it's increasing a
So we have
lot.
already seen that 100% on Socrates. Let us see whether you can reach 100 likes soon.
That's a great game.
Yes.
That's a really nice game. But what happens? So I got the, is it the, because every now and then these commercials comes in. How can I avoid these commercials?
Commercials?
Yeah, commercials. How is it?
No.
No, no, it was just a mistake here. Okay, so now we're gonna go.
Okay.
All right. Thank you, Mustafa. Okay, guys. So what do you say when you do this? You say respect, respect. Some of you guys were already wondering like what's up? What's special today because I'm dressed like better than usually. I'm here to celebrate your life, success of your life. Because what's going to happen today is that we're going to go all the way up to the summit of the big mountain. The name of the mountain is called Simulation of a Mechatronic Machine. That's the major size mountain, and today it's going to happen. So we're going to discuss the subject matters that is going to be so difficult, so complicated, so theoretical aspects that if you're going to manage, I mean, if you understand 5% what I'm going to say today, 5%, 5, not 50, but 5, you can congratulate yourself and you need to give a serious credit to yourself. Something you can make your life to be super wild, like extra cup of coffee. I don't know, something crazy like that. So we'll see. But 5% of what I'm going to say today, if you understand that, that's a lot. That is going to be a lot. And rest of your master level studies will be downhill, boilerplate. It's going to be simple. So it's going to be if you manage today, you're done. You can congratulate. Okay, it's just a little bit of formalities, and I'm good to get my master degree. Okay. Mustafa, by the way, said the really nice, really nice competition. He said that if I'm able to collect 100 thumbs up in my YouTube channel for this recording, or let's say this streaming, it's going to be one extra point for each of you. Think about that. How you guys like? But you need to, I think that you can only give a thumb up if you're registered in YouTube. Is that correct? But I want to change my profile from a professor to be an influencer. Have you heard about that? So if I influence in the 100 people, that is already considered as a serious influencer, isn't it? Pretty much. 19, 19. Okay, so we're still a little short from 100, but is it increasing? 100 tons up. Okay. Yeah, I'm not going to call the rector. How much?
22.
22. So I'm not going to call the rector because of that. But if there's going to be success rate, today, seriously, if there is 100% success rate in today's in-class quizzes, for sure I'm going to do something special. One year I was doing dancing. Coffee for everyone. That could be the way to go. That could be my. So if you're going to score 100% today, coffee for everyone. On me. Okay. Oh my God, I'm losing money big time in this class. So that's a high risk game, very high risk game. Okay, what's going to happen today is this. So we continue to discuss about virtual displacement, virtual work, and not those concepts so much because we wanted to do something with these concepts. And what we wanted to do with this concept is called generalized externally applied forces. And as the title implies, that's the force component that is imposed to generalized coordinates. And that's something that we need to discuss. We need to look at a little bit of examples today, but the same thing than generalized coordinates. So everybody needs three generalized coordinates. So now if the force is imposed to the body, this body needs to be divided to three coordinates because these are the coordinates that define the body configuration. So we have to express forces using the same space. That's a little bit fancy word, but let's say the same space than how is the configuration of the body. Body configuration is based on three coordinates. Forces have to have three components. So that's what we're doing. And these three components are associated to generalized coordinates for a single planar body is Rx, Ry, and angle theta. And that's what we're going to do. Most of the cases, the forces are initially imposed in global coordinates, like gravity force is a good example, but we have to convert the gravity force from the global coordinate system to be expressed by using generalized coordinates. Why? Because we need to be consistent, and we started to be consistent from the kinematics. We concluded that we're going to describe the particle using the kinematics that is based on three variables, generalized coordinates. So that's what we're going to do over and over and over again. Okay. All right. So why I say that this is one of the nightmare classes in your life? That's simply because you learn that it's a little bit involving to express generalized external applied forces. Those are kind of symbol forces because those are like force vectors that are somewhat understandable to convert to be expressed by using generalized coordinates. Now what's going to happen today is that we're going to also express our inertia forces in terms of generalized coordinates, in terms of three components. This is mathematically extremely complicated. My recommendation, don't take a look at that. Let me rephrase. So don't get confused about the mathematical details because mathematics is here, mechanical tool to help us to complete what we wanted to do. Nothing but the mechanical tool. So let's take a look at what is our overall expression. That's what interests us more than the mathematical way to reach this, the final destination. Okay, that's what's going to happen today. But the first thing first, what is that we discussed a week ago? So a week ago, we made our first analysis. And the first analysis was kinematic analysis. Kinematic analysis can be conducted if and only if the number of degrees of freedom is 0. Correct. Why it needs to be 0? Because we have to have a matching number of equations and unknowns. What are the equations? Equations are our constraint equations that are limiting the motion possibilities of the system. Those are called constraint equation, and we can have constraint equation that limits the motion possibilities of two neighboring bodies, like the revolute joint is a good example. Or we can also have a driven constraint where there's a pre-described motion that we have to obey as well. Constraints, joints, are the highest possible power in the universe. There's no way we can break them because they are like mathematical notations. Forces are much weaker than constraints. Constraint we have to obey no matter what. Okay, right. So equations are a number of constraint equations. What equations are coming from the constraint. Unknowns are generalized coordinates. We need to get equal number of unknowns than number of bodies in the system. Number of bodies in the system multiplied by 3 because everybody needs 3 generalized coordinates. Where these 3 generalized coordinates are coming from is coming from our kinematics. Kinematics, the one that we are repeating over and over again, this equation R plus rotation matrix multiplied by vector U bar. So these are the 2 components. Here comes the angle theta. These are our unknowns. Okay. Now, kinematic analysis. So it consists of 3 steps. The first step is a position analysis, which is the hardest to conduct. It's hardest because we need to use an iterative approach to make it happen. So we are not able to get the solution directly, but we need to repeat the iterative procedure a certain number of times until we're happy about the accuracy. And it works in a way that we compute something that is called Newton difference. A Newton difference, you can get it once you inverted your Jacobian. Here's another evidence that we have to have an equal number of equations and unknowns, because only in this case the Jacobian matrix is skew in size. Because Jacobian matrix, you can get it by taking partial differentiation of your constraints with respect to your unknowns. And you can only invert it if it is skew in size. Okay, then you're going to get the Newton difference. With help of Newton difference, you can get the better guess to your position level generalized coordinates. You redo it, you're updating your constraints and your Jacobian. You compute another Newton difference, you will get the better estimation. And you do this until you're happy with how small is a Newton difference, or there could be different kind of iterative, how to close this iterative process. But anyways, you do this until you're happy with the accuracy. Then you move on to the next level, which is the velocity level analysis. Simplest of these three analyses, as is only a simple substitution. And then you're moving on to final level, which is acceleration level. That too is based on substitution, is no longer as simple as the substitution in the velocity level, but it's doable. So that's what the kinematic analysis is about. And then you're increasing the time and you redo it. So that's the way to solve it. All right, so this is the procedure and the position level, pretty much what I just explained, so I'm not going to do this again. So then we moved to completely different era. And the completely different era was dynamics. So we left kinematics behind, and we started to discuss about forces. Remember this, kinematics, there's no words about forces. It's just a motion analysis. Dynamics is all about forces. And actually, we, in a simple life, we have only just the two different kind of forces. External applied forces, which could be like the one that are coming from different kind of actuators, hydraulic actuators, pneumatic actuators, electric drives. Those are the forces that are applying the system externally. And then inertial forces. So these are the two different types of the forces. In addition to these two different types of the forces, we could also compute something that are called reaction forces due to the constraints. But let's leave those a little bit aside for this time. And let's just consider that we either have external applied forces or inertial forces. And now what we're going to do is that we're going to set these two categories of forces to be equal. And that's going to give us dynamic equilibrium. Once we know the dynamic equilibrium, also known as equations of motion, then we can solve these equations of motion in forward of time. Okay, you guys still with me all the time? You can follow my reasoning here. Okay, good. Now, the first thing was, how is that we can express our externally applied forces in terms of generalized coordinates? And you see that the problem is this. If you have a force component applying in a global coordinate system like this one here, and then you wanted to express that by using this set of coordinates, even the numbers are not matching, because the force vector consists of two components. There are force component with respect to global x and force component with respect to global y component axes. All right, what we're going to do here is that we're going to introduce something that was called virtual displacement. And with help of virtual displacement, we can actually create the relation between generalized coordinates and global coordinates. And more accurate, actually, is the other way around, from global to generalized coordinates. And it happened like this. So once we introduce a virtual displacement to this guy here, so we call this delta r, and we know that delta r can be written like this. And because of that, we know that the r is a function of generalized coordinates. These generalized coordinates in a simple case is rx, ry, and angle theta. Okay? Now, following the mathematical rules, we can express this delta r in such the way that it is partial r partial q, because this relation multiplied by delta q. Here's our relation. So okay, this sounds like very mathematics that is having no relation to real life. But yes, there is something important because this component here, which is this vector here, consisting of two components with respect to global x and y-axis, which is obviously global coordinate system, can be now related to this guy, generalized coordinates. And relation comes from this partial differentiation. Now, with help of this mapping matrix, if you may, I can actually express this force in terms of generalized coordinates. Now, there's going to be soon. There's going to be two in-class quizzes. The first, I'm going to asking, what is the role of this matrix here, this mapping matrix, that relates global coordinates and generalized coordinates. That's what it's doing for you. And then I'm going to ask you a symbol mechanism is actually a one moving body only. I'm giving you several options. How is possible? How is a vector of generalized coordinates? First thing that you need to look, what's the number of options? So number of options for the one body need to be 3. So if there's an option that there's a 2 force components, is obviously incorrect. And then you just need to look at a few other details that I'm explaining you momentarily, and then you're able to answer this correctly. But the first question is, what's the relation between, what is the interpretation of this mapping matrix? It is mapping global coordinates and generalized coordinates. This in-class quiz, by the way, is already on. So you can, if you want, you can already start answering that. And you can change your answer if you are not yet fully convinced what is a correct answer. Okay, here's going to be our final destination. This is how the equation of motion will look like. This is going to be like that. This is where we're aiming for. So how much we understand so far? So let's circulate the components that we're already familiar with. Okay, obviously there's one good friend of us, this guy here, Jacobian matrix. That's something we are already familiar with. And the Jacobian matrix is here with the transpose operation, so that's something we are familiar with. There's something more we know. We also know this guy here, because this is an acceleration of generalized coordinates. So we know what they are standing for. And then new guy that we kind of know. We are not yet sure if we know this well, but somebody that we are kind of familiar with is this one here. This is a vector of generalized externally applied forces. That's what we get to know momentarily. We're still lacking few components. We're still lacking this guy, which is a mass matrix. We are not sure what is this Lagrange multipliers, what is their role. We're going to introduce that next week, not this week. And then, of course, this one here, which is a quadratic velocity vector related to mass matrix, let's say the inertia component. And this is something that is coming when we're converting this, when we express in the equation of motion. So it's related to constraint equations. Okay, those are the components. And now what follows is that we're going to redo the whole story about generalized external applied forces rapidly, because I feel that you need to learn this, you need to hear this one more time. And once we're done, then we're going to practice it. Okay. Again, one more time. Here's the deal. So we wanted to convert this force component to be expressed by generalized coordinates. And we're going to do this by using a concept of virtual work. And concept of virtual work is like this. Virtual work is equal than the force multiplied by virtual displacement. A virtual displacement can be expressed pretty much like I just explained. So there's a delta R, delta Q, this relation. And once you submit this relation here, what's going to be left, and what's going to be your conclusion is going to be like this. Delta Q. Now this component here actually takes your external applied forces and express that in terms of generalized coordinates. So this is going to be the one that is called as a vector of generalized external applied force. The one that you hear in equation motion is this guy, this one here. All right, so that's how it goes. Now the middle steps, or the kind of the component that is handy in the middle, is to do this differentiation. This mapping matrix, this magic mapping matrix, this is partial R, partial Q, in detail as it is shown here, because this is going to give us something like simplifies the notations in future. And something that simplifies the notations in future is this matrix that we are actually familiar with. Remember, we met this guy when we discussed about velocities. So this is a rotation matrix, rotated 90 degrees angle in a positive direction. And then we have here vector U bar. This is a good friend of us, so nothing new in that regard. And that's it. Okay, now, once you multiply your force with this component, this is how it looked like. Now, the simple force component, like, give you an example, like the beam like component where the gravity is applying here in the center of the mass in the middle. This force will be expressed in terms of generalized coordinates, and now how it will be expressed depends heavily where the body reference coordinate system is located at. Let's say that the body reference coordinate system is located in one end of the beam-like body, like here. What are you going to do then? Is that you kind of take this force, you impose it to apply in the origin of the body reference coordinate system. And because there's a level arm, this much, you take this level arm into account by using this third component. You see that this is vector U bar where the force is applying. This is rotation matrix, rotated 90 degrees angle, and the force. So this is obviously a moment that depends on how far off is the force from the center, or let's say origin of the body reference coordinate system. Sometimes the silence is more effective than anything else. You guys know that. Because immediately they got your attention. I noticed that you started to fall asleep and you were thinking, when I'm going to leave here, first I'm going to go to liquor store and then I'm going to go to grocery store. No, first the grocery store and then liquor store. But now you need to listen to me again. Okay, so let's just do whatever you wanted to do after this class. Let's focus on this matter, okay, because it is important. All right, so we're kind of moving the force applying in origin of the body reference coordinate system, and we take the moment into account. And the moment is level arm multiplied by force itself. The moment is always a scalar component. You know that. This one here, when you do the math, it is actually a scalar component. This is a vector, exactly the one that the force is applying wherever it is applying. So that's what it is. So let's look at this one more time. But the mathematic component was this guy here that relates global coordinates and generalized coordinates. All right. So here's the forces. So if I have the force applying any particular point in the body or even outside of the body, it's the force component. This is these two components, and this is the moment. So this is actually a scalar component once you do the math. It's clear because this is going to give you a vector, and this is going to be a vector. So what is left is going to be scalar component, moment. Maybe that's the more something that you are used to deal with. All right, so my first in-class quiz is this: physical interpretation of matrix, partial R, partial Q, in case of virtual work. And the options are: defines relationship between the global coordinates and constraints. Constraints. Seriously? Constraints? All right, defines a relationship between the constraints and generalized coordinates. Here's the constraints again. Okay? Defines relationship between the global and generalized coordinates. Defines relationship between external applied forces and constraints. All right? Let me revisit that in a moment. So let me continue the story here. So let's look at an example here. So here is an example which is pretty much what I explained to you. So I have here a beam-like body. There's a gravity applying in the center of the beam-like body. And then body reference coordinate system is not located in the center of the mass. It's not. So it's outside of the center of the mass. Okay, so let's compute vector of generalized forces. So it's going to be obviously this force component as it is, two first components. And then what is going to be left is going to be moment arm. Moment arm that is going to be a function of the rotation coordinate, obviously. Because, if the body is rotating like this, level arm will be 0, as is also the case. If you think about that there is a beam-like body, sorry about the low quality of the drawing, and the body reference coordinate system is located in the middle, and the gravity is applying here. The moment arm will be 0. 0 because level arm is 0. Okay. All right, so let's continue then. All right, so here is the equation that I learned from the previous equation. So I have my rotation matrix that is a rotated 90 degrees angle, and then the vector u bar. So this is a clear, simple matter of a substitution. So once I do the substitution, I'm substituting the vector u bar to this equation. So vector u bar, by the way, because the body reference coordinate system is here, and x-axis is pointing upwards, is going to be L divided by 2, 0. And once I do this substitution, my mapping matrix reads like this. Once I do the math, you see that, okay, I got 0 component in a x-axis direction, which makes sense. Mass multiplied by gravity constant as my y component, minus direction. And the level arm, that depends on what is an orientation. So how far off travels this force? So if it is like this, it's going to be full maximum length, which is L divided by 2. If it is like this, it's going to be 0 because it's traveling to the origin of the body reference coordinate system. All right, that's what it is. Now, what about this? What about this case? What if I'm going to have the exactly same body, but the difference comparing to what we looked a little while ago is the fact that now body reference coordinate system is located in the center of the mass. So you need to take a look at how big is a level arm, how big it is. And then you need to pick the components, or you need to pick an option where there's a appropriate number of components. Here's a hint. Everybody needs, yes. That's what the first thing you need to look. And then the last thing that the second thing you need to take a look, how is a level arm? Okay, it's not yet on because I need to take a look at the first in class quiz. What did I promise as a reward? Coffee on me. Coffee. It becomes to be expensive to deliver lectures. Well, we'll see. I guess that is not going to be. I actually trust that I'm losing no money today. Okay, so here we are. So let's take a look. Hold on. Not this one, but this one. 120 students. Okay, I'm a little worried because a week ago it was 130 something. It's increasing. Okay, I'm okay. I'm okay. Okay, I see that the options are a difference. So because it defines the rotation of the particle, defines the body dimension. So these texts are different that is in my PowerPoint presentation. Sorry about that. But again, we have our good friend of rotation of particle, defines the body dimension. And the option that is correct is still here, like same way that it was in the slides. And the success rate is, oh my God, I need to be careful here. Because 130 coffees is like 100. Oh my God, it's my month salary. So, whew, whew. Okay, the next one. This is, I'm not going to give you any hints whatsoever. Absolutely no hints. Okay, you don't see how it is. So you need to take a look at this again. Take a look at this. Absolutely no hints because what if you guys are scoring 100%? I would actually like to increase the stake, but I don't do that. Like lunch on me. What's that? Yeah, not that. Okay, so what do you guys think? Which is the correct answer? Yeah, only there are two options which consist of proper number of components. So others are out. So then it's about how big is a level arm. Yeah, it is. It is. You're absolutely right about that. Who is this WhatsApp officer? Was it you that is controlling the WhatsApp? No, WhatsApp. Okay. Are they people are saying anything in the WhatsApp? Like, what is the correct answer? Are they? They are. They are. There is a poll. So can in a WhatsApp you can set the poll. Really? That's a really clever thing. Can I take a look like how he reads? I, really?
Yeah.
So how can you did not invited me to participate? So you feel like a little bit outsider. Okay. Okay, you guys have become to be good in this business. So let me see how we got very few number of answers. So only 80. Okay, it's increasing now. 80, 80, 88, 91. So soon we're gonna break the 100. Let me see how many thumbs up we have. I don't even. Oh my God! Is this really
36.
36? Yeah, that's a lot. Yeah, 36. 30, 37. 37. Okay. Ah, okay. So it's not even possible to have 100. But you guys are. You could use your phone to thumb up. Okay. Anyway, so we here. So we got 110 answers. 100 and. Okay. So I think we're gonna close this case momentarily. What about because otherwise this is hard. You need to see these options. So I'm gonna close this. 113. It's a little less than last time, but the correct answer is A. Correct answer is A, obviously. Ooh. Okay, I think that I can start. I'm off the hook. I'm relieved. I think that I can save some money, so I don't lose money anymore when I do these lectures. Still, the percentage is very high, so it's 88%, so it's extremely high percentage, but we're still far from 100%. Okay, let's continue then. Okay, let me show you another example, and then we're going to move on to these inertia components. Ah, sorry, this needs to be this order. So first this one, and then this one. Right. Okay, let's look at another example. So we have here a body that is a triangular in shape. This is a little bit confusing example because forces that are applying in two corners of the triangular shaped body are expressed in terms of global coordinates. So you need to understand that they're pointing this direction no matter how is the configuration of the body. So it's like pretty much like if you have here a point force like this. Even when I'm rotating the body, the point force still remains the same orientation. So it's like this kind of configuration. That's how it behaves. All right. Now I have a one force that is applying in a corner called A, and then I have another force that is applying in a corner called B. All right. So what I need to do is that I need to express these points using the kinematics that I'm very much familiar with. So I'm going to do this in a hard way. So I'm going to express this point and this point by using this kinematic equation. All right. What I'm going to do afterwards is I'm going to differentiate this, which is called R. I'm going to differentiate this R with respect to my generalized coordinates. And it's going to give me this magic mapping matrix. What is left to do is that I need to multiply my forces, which is this one and this one, by this magic mapping matrix. And I'm going to get two set of, well, let's say, two pieces of forces that I just need to sum it up because they're applying in the same body. So that's what I need to do. Okay, let's continue then. So the first thing first will be kinematics at the point I. So that this corner here, how can I get this? So it's going to be very simple. I can take the components from the vector u bar, simply substitute it here, so 1 and 2. And then this is my rotation matrix, my R matrix. So this is the two components that I'm going to get. Once I differentiate that with respect to my generalized coordinates, and one more time, generalized coordinates are Rx, Ry, and angle theta. I'm going to get this kind of the mapping matrix. So this consists of 2 rows, 3 columns. 3 columns because 3 generalized coordinates, 2 rows because of the 2 global coordinates. Okay, now what is left is that I need to map my forces with help of the mapping matrix. I'm going to get the 3 components. Components as they are, and the level arm, let's say the moment component. Moment component would be the better way to say that. And that's it. Then I redo the same, but for point B. The point B is located here. Actually, only difference here is that the vector u bar will be different. So here's my vector u bar, and this is going to give me 2 components. Once I differentiate that with respect to my variables, generalized coordinates, this is going to give me a second set of external applied forces. They are applying in the very same body. So what I need to do, I need to sum them up. And once they sum that up, this is how it looks. My first component, second component. So this is my finally generalized externally applied forces. Okay. Very, very mechanical. Take a look at the number of components. That's what matters the most. Okay. Simple thing. Okay, the moment. If there is a moment, that's going to be simple because any moment you have in your system, you just added that to your third component, your angular component. So moment, that moment you can move as you want. So this is if you have any additional moment, you just sum it up, whatever is your level arm. So it's pretty straightforward component. Okay, now, moment of truth. You guys ready to see something that is going to be, you're going to see nightmares about this stuff, years in, years out after, I'm going to introduce this to you because it's going to be so complicated that there's no limit. You're ready for that? You're absolutely ready for that. Okay, what about this? You still have can-do attitude. Okay, so let's get in the top. So it becomes to be this serious. Okay. So, generalized inertia forces. That's what we're going to do. The concept, well, this is a level of difficulty. This I already explained. So this is LD, level of difficulty. These are the lecture numbers, 1, 2, 3, 4, 5. We here. So we started like this, sometimes negative. This was a little peak because of the kinematics. And now here's a summit. This is a summit that we're going to go top of the summit and the rest like this. Very, very enjoyable, downhill all the time. Soft stuff. Okay, here's a mission. This is what we wanted to do. That inertial force is, like we discussed earlier, is mass multiplied by acceleration. Now, acceleration, sometimes you have seen this, that the acceleration is like mass A. This is standing for acceleration. And when you look at your lecture notes from your bachelor level courses. Now here, instead of A, we're saying R dot dot, but you understand that there's no difference. And instead of mass, we want to show off about how good we are in physics and mechanics. So instead of saying mass, we wanted to say that, okay, the mass is equal then integral over the volume of the body and the density. That's going to be our mass. Okay. So this is kind of important because remember where we started. We started that there is a body like this. And body consists of particles. So what we're doing here with this volume integral is that we're collecting the information from each of these particles. And what we really wanted to know from each of these particles is their density. That's, once we know that, then we can compute the mass. Okay, this is not so, this is maybe overly complicated way to say the mass. But just to sake of generality, it is expressed as a volume integral. Okay, you're still with me? Okay, now this guy here is no good for us. It's no good for us because, this vector r is expressed in a global coordinate system. So here's our vector r, this one here. When you differentiate that once with respect to time, you get r dot velocity. Second time, you get r dot dot. But it's not going to change the number of components. The number of components remains same all the time. So here, when you started is 2, velocity is 2, acceleration is 2. So that's not what we're going to use here because we have to convert this to be expressed by using generalized coordinates. All right, so how we can make this to happen? Of course, we're going to use our good friend D'Alembert. D'Alembert, we discussed this earlier. What the D'Alembert was saying was that inertial forces can be treated exactly the same way than external applied forces. Exactly the same way. Really? So if that's the case, let's treat them exactly the same way. So let's use the concept of virtual displacement, virtual work for this another type of the forces, and let's compute how is a generalized inertial forces based on that concept. Okay, so this conversion from 2 components here to 3 components here is going to be based on virtual work, virtual displacement to be more specific. Okay, let me take a look. So it's still a few minutes before the break. So we're going to get started, then we're going to have a break, and then you guys relax and you come back. But you know what we're aiming for here. You understand what we're aiming today. Okay? That's clear. All right, so it's mentioned here that following the D'Alembert's principle, the work done by inertial forces can be expressed. Virtual work done by inertial forces can be expressed like virtual displacement, inertial forces. And inertial forces is nothing but mass multiplied by acceleration like this. Okay, so I'm going to substitute that information here. And this is how my virtual work done by inertial forces look like. Okay, I continue my story. Then I'm going to use this relation between the global and generalized coordinates. This relation we discussed earlier, that the one that is coming from mathematics that relates delta R and delta Q. Relation is this magic mapping matrix. So once I introduce this mapping, I'm going to get something that is called generalized inertial forces. And generalized inertial forces is volume integral over the density by mapping matrix, and then acceleration. Now this is not great yet. And this is not yet great because what I'm after here, what I really would like to get a hold on is my generalized coordinates. And now that generalized coordinates are unpleasantly hidden to this component and here too, but they are not explicitly expressed. And this is going to make me hard to solve the equation of motion because I would like them to be explicit. So what I'm going to do is that I'm going to play with the math. So first, I'm going to express my acceleration using reorganizing my different components. We learned, I think this was the second class, we learned that the acceleration consists of three components. This is a translational acceleration. This is angular. Oh, this is a typing mistake. Here, the two definitely shouldn't be in this equation. So this is angular acceleration multiplied by this rotation matrix that is rotated once with respect to, 90 degrees angle rotated rotation matrix and with the U bar. And then this one here. I think, by the way, that there is another typing mistake here. This one here, my apology, because this obviously, yeah. Oh no, no, there is not. That's how it is. That's how it is. Okay, now I'm gonna express this in a way that I'm gonna put my acceleration components, generalized acceleration components as a own vector, and whatever is left is gonna be something that is a matrix that will be multiplied by my acceleration. And then the last component left is gonna be the components quadratically related to velocities. So this is just a reorganizing my acceleration, okay? Now I'm gonna substitute this reorganized acceleration to this equation. I'm gonna substitute also this mapping matrix to my equation like this. And when I do this, this is how it looks. This is my mapping. This is my acceleration. When I do the math, there's gonna be two components. The one which is called mass matrix, which is going to be linearly related to my accelerations, and something that is called quadratic velocity vector. This is going to be my generalized inertia forces. You see that the mass matrix here is related to my generalized coordinates. So obviously for one body, the mass matrix will have a dimension 3 by 3. Quadratic velocity vector is something that we don't need to worry this time. Let's get back to that a little later. There are ways to simplify our quadratic velocity vector. Actually, for your information already this time, quadratic velocity vector becomes to be zero vector if body reference coordinate system is located in the center of the mass. But it doesn't need to be there. Certain commercial code, they prefer not to put the body reference coordinate to center of the mass. That's their choice. Okay, so that's what we're gonna look next. But first thing will be, guess what? Yeah, break. Let's have a break. And then you're gonna look at what are the components inside of the mass matrix? How is a quadratic velocity vector? And that's it. That's gonna be everything we need to do today. There's gonna be another in-class quiz about mass matrix, a little something about quadratic velocity vector, and then we are almost there. Almost there is this equation of motion. We are not far from that anymore. Remember, this is how the equation of motion will be written. Mass, Jacobian matrix, Jacobian transpose, 0. This is acceleration, Lagrange multipliers. Up. Oh, I'm writing out of this space. We just learned this guy. We know this guy already. This guy already. This is what we know. We know this and kind of this too. So it's not much left. Almost there. Okay. So it's how much you need to recover from this? 10 minutes. 10 minutes. Okay, 10 minutes and then we will be back. Okay? Hold on, I'm gonna put this video capture. This one I need to put it off. Okay. Ei ole väliä. Voi olla mistä järjestyksessä tahansa, kunhan pysyt vaan sitten, että kun olet kerran valinnut sen järjestyksen, niin sitä ei saa enää vaihtaa. Oliko se sitten sellaisia vaihtoehtoja, että ne on niinku erilaisia? Ne...
Eri järjestyksessä, mutta samat vaihtoehdot. Että siitä tuli vaan, että se ei ollut akkosjärjestyksessä ratkaisu siinä tehtävävaihtoehdoissa.
Joo, se on kyllä vähän epäreilu, koska se on ihan oikea, vaikka se...
Niin, tässä oli tehtävä niin vaihtoehtovastaukset, kyllä se löysi sen oikean vastauksen, mutta se vaan, että se järjestys
se voi vähän... Ei ole väliä, joo. Ei ole väliä.
Joo, sitä mietin, että se ei ollut akkosjärjestyksessä.
Joo, ei ole. Joo, sitä muuten ei ole kyllä koskaan puhuttu, mutta että se on ihan ok. Se voi vaihtaa mihin järjestykseen tahansa, mutta sitten kun laskee vaikka Jakobia ja muuta, niin sitten se pitää pysyä vain niin yhdenmukaisena.
Niin, että se jatkaa samalla.
Joo, samalla.
Jatkuvasti, mutta
niin
sillä ei ole väliä, että miten sä lähdet.
Ei ole. Move this force apply here, this force here, they could cancel themselves as a two first component, but moment arm need to be accounted. So it's going to be something that, this vector here will have a first component 0, second component 0, but then the level arm you just need to take it into account. Okay. The moment component will be non-zero. You got it?
Yeah, I got it.
Okay.
So the direction of motion matters.
Yeah, yeah. So it's going to make this body to rotate.
Okay.
So it's not moving anywhere but rotating.
But
rotating, yes. Okay, guys, what do you say? Are we good to go again? All right. Another mistake, because it's a certain order that I need to follow consistently. Otherwise, this is not going to display for you guys. Okay. We were here. One more thing. Here and now. Okay, so now what's going to happen next is that we're going to take a look at the details about the mass matrix and details about the quadratic velocity vector. So they two together, they're going to be something that is called generalized inertia forces, as they are applying to generalized coordinates. So they will have a total of 3 components. There's going to be translational components, 2 of them, and also the third component that is applying to angle theta. So that's what they are. And now the only thing kind of left for us is that once we have these generalized externally applied forces, then we're going to have this second component, which is mass multiplied by acceleration, and then was a minus this quadratic velocity vector. This is going to be kind of our equation of motion. You see that this is what we're looking for. This guy is that we are after. So we wanted to express the acceleration of generalized coordinates explicitly, something that we can integrate in forward of time, because this is what we're going to solve. So we're going to get from acceleration, we're going to get the velocity, and velocity, we're going to get the position. That's how we're going to go. So it's like an opposite direction that we did in the case of kinematic analysis. Now we started from acceleration. From acceleration, we're going to integrate velocities. Velocities, we're going to integrate the positions. Then we're increasing the time, and we redo the whole procedure. Okay, but this guy, and this guy in details is not yet explained. So let's take a look then. So let's take a look how they are. And that's, we're going to get started from the mass matrix. Okay, the mass matrix, like I mentioned, consists of 3 components. And now I'm categorizing them in such a way that I have like 3 different components here. So this is 3 by 3 matrix. One is the component, or let's say the submatrix that is located in upper left corner. Yes, sir. Is how come it's not in YouTube? So what happened in the YouTube? So it's black again. Hold on. So I think it was the same problem a week ago, wasn't it? Oh yeah. Of course it's black because of this. Okay, I need to do this. No, still is black. Is it? Is it black still? No. It's back. It's back. Yep, it's good. It's good. So I wanted to explain about this mass matrix. So the mass matrix has a dimensions 3 by 3 because of the 3 generalized coordinates for each of the bodies. Okay. Now, what is located here in the upper left corner of my 3 by 3 rotation matrix is called identity matrix. So the subindex 2 refers that this identity matrix consists of, that is having the dimension 2 by 2. So this is obviously a matrix like this. So remember, the identity matrix is something that the diagonal components are equal to 1. Off-diagonal components are equal to 0. So that's what it is. So that's my identity matrix. But look at this. So my identity matrix will be multiplied by when you integrate the density over the volume of the body. Okay? Then there's going to be a component that translates, or let's say combines translation and rotation. This is having no clear physical interpretation. The component that will be 0 if the body reference coordinate system is located in the center of the mass, but not having any clear like physical interpretation or any clear names or anything like that. It is related to quadratic velocity vector. And then the last component, which is actually a scalar component, is going to be something that you guys all know. So you have seen this multiple times before, because look what it is. So if you look at the details of this component, it can be computed like this. This is obviously mass moment of inertia. Mass moment of inertia. So how much inertia resisting your motion? There is this, simple famous case is that, if you have a beam-like body and the body reference coordinate system is located in one end of the beam-like body, resistance is much higher than if the body reference coordinate system is here in the middle. You can test this by taking a beam and rotate it like this, or rotate it like that. You can feel the difference. Well, I can feel the difference easily because I have such a big muscles, but I'm sure you guys can easily see the difference. Okay? Okay, so that's what it is. So it's a mass moment of inertia imposing to one coordinate only, and the one coordinate only is angle theta, because that is our rotational parameter. Okay? All right, so these are the components. And how is it we can compute each of these components? Yeah, we can do it in a really complicated way by using these volume integrals. If you really want to torture yourself, that's a fantastic way to make you really feel the pain. But if you want to, make a life a bit more enjoyable, then it's highly recommended to take these components from pre-calculated tables. There are pre-calculated tables for mass moment of inertia. Other components are not necessarily needing any kind of computing whatsoever, because once you do the computing of this 2 by 2 matrix, what's going to be in the diagonal components is the mass of the body. Because mass of the body is going to have the same resistance, translational mass, if you're moving this direction or this direction. So it's all the time same. That's why it is a diagonal matrix, and that's why the components in a diagonal are same. So it's not that the resistance is harder if I move here than here. That's not this planet. You got it? Something that people often get very, very confused, and it's going to be my next in-class quiz. How much the body weight, the mass of the body changes depending how you measure it. Because we can put this body reference coordinate system anywhere we want, within the boundaries of the body or even outside of the boundaries of the body. And now it's going to affect how is a certain component in the mass matrix. So it's going to affect this component because mass moment of inertia will depend where you're going to measure it. Also, this component that translates or relates translation and rotation is going to be changed. But this component, which is the mass of the body, it doesn't matter how you measure it. It's like if you're going to measure your body weight by using left leg or right leg, how much is the difference? How much I can lose weight? If I can go to diet by first measuring my body weight by using my left leg, and then almost immediately after I will do my right leg. What's going to be my body weight? Same, of course, it's going to be same. So this is not going to be affected by that. Mass moment of inertia, yes, that's going to be affected because it depends which is the coordinate that you're going to you're going to rotate your body with respect with. That's why this is going to be changed. And that's why this component that translates the rotational translation will change as well. But the body weight doesn't change. So what I'm going to ask is an in-class quiz that how much the body weight, how much the mass of the body will change when I'm moving my body reference coordinate system from one coordinate to another coordinate. The answer is not changing. Not changing. Okay? All right. Now, here we are. Let's practice. Let's take a box like body. Let's compute each of these three components. So what I can recognize already that the component that relates translation and rotation is going to be 0. How can I know that? I know that because the body reference coordinate system is obviously located in the center of the mass. So this component, this one here, is going to be equal to 0. It's actually vector. Vector of two components is going to be equal to 0. Okay, but I can demonstrate that by using this very, very sophisticated volume integrals. Okay, so let's do this in a hard way. Let's do the volume integrals. Volume integrals, I need to do that with respect to 3 axes because of the volume consists of 3 axes. Okay, the first axis that is not mentioned here because I'm dealing with the planar space here is width. So I'm going to simply put W here and multiply W with the density of the body. Okay? What is left is still my X and Y component axes. So what I need to do here is that I need to take my volume integrals such that x-axis is x-axis is getting started from minus L divided by 2 and it ends L divided by 2. Here This is L divided by 2 minus, and it ends here, L divided by 2. The same with the H direction, which is here, minus H divided by 2 until H divided by 2. Okay? So that's what I need to do. So I'm going to first integrate this X direction. So it's going to give me L inside of this component, and finally this H direction, which is Y direction, it's going to give me HLW. This is equal then volume. Volume multiplied by density is going to be mass. Okay, that's multiplied by identity matrix, which is this guy here. So I'm going to get the 2 by 2 matrix where the mass of the body is located in a diagonal components. Don't do this in this hard way. You don't need to torture yourself with a math. Just take the mass, put it in the diagonal component, that's it. Okay? What about mass moment of, no, the one that is combining translation and rotation. So here's my rotation matrix, difference rotated 90 degrees angle, then my U bar vector and density. Because here in the middle, you see that this obviously is going to give you 0. It's obvious case. Because I have equal amount of like linear components, so when I'm summing this one and this one, they will cancel each other. That's what's going to happen in integration procedure. So that's why what's going to be left is 0. It would be a different story if I would place my body reference coordinate system in a one corner, because there is nothing that cancels themselves. Okay? So the last thing left is a mass moment of inertia. And again, please use pre-calculated tables to get this last component. So I'm going to use this in a hard way. So this is my vector u bar x power 2, vector u bar y power 2. And then I'm integrate this in x and y direction. Once I do this in x direction, it's going to give me like this equation. I'm not going to show you the details, but please take a look at the use a symbolic math tool. I can see that dy is missing this part. So once you do this component, this is what you're going to get. M divided by 12 multiplied by L power 2 plus H power 2. Typically, when we have a very thin-like body, this component is insignificant, and you can ignore it. Okay. Are you guys still with me? How hard it is being? Really? You said that it's like manageable. Are you guys thinking that this is manageable? You lie. This is harder than manageable. Much harder than a manageable. Isn't it? Like pure torture. Like from beginning to end. Okay. But as promised, this is it. This is the hardest in your entire course of master degree. Rest is going to be boilerplate. Okay. Let's continue then. Let's summarize. So this is how the mass matrix look like. So I'm going to take these 3 different components. This is the part that is related to this corner, upper left corner. This is my mass moment of inertia. And what is left here was 0 vectors. Okay, that's it. Let's redo the whole thing, but let's make our life more complicated. Let's make a life more complicated by moving the body reference coordinate system to one corner of the box-like body. All right. Bad news. Bad news is this, that the component that relates translation and rotation is going to be non-zero. How I know that? I know that because the body reference coordinate system is not located in the center of the mass. Because the integration, definitely there's going to be non-zero integration because there's nothing that cancels themselves. So let's do it. How much is going to affect the weight of the body? No effect. Absolutely no effect. So even when the integration limits are different, now I'm integrating from 0 to L, 0 to H. As you can see from the integration limits, Makes no difference. That is still going to be the same amount of mass from both of the cases, regardless where the body reference coordinate system is located at. Okay? So I do the math. So I get here a volume again. Volume multiplied by density is going to give me the mass. Mass multiplied by identity matrix, no difference. Is it going to affect my mass moment of inertia? Yes, yes, because now the inertia resistance is going to be different because I'm rotating this with respect to different corner, let's say the different position than in the previous case. So is it going to be bigger or lower than in the previous case? Bigger, because the resistance will be bigger. Okay, so let's do it. So let's take the first thing, let's take this component that relates to translation and rotation. Oh, this looks very, very bad. So I'm going to take this rotation matrix off from the volume integral. So what is left is this guy. So then this guy, I'm going to simply integrate this. I'm going to first take this W into account, and then I'm going to integrate this from X and Y direction. When I do that, it's going to be non-zero. Definitely non-zero, because this is like a linear component. A linear component from 0 to something going to give me non-zero solution. I'm going to do this in a Y direction. So once I will do this, this is what's going to be my final conclusion. That's multiplied by the rotation matrix, rotated 90 degrees angle. That's going to be my two components in my vector. No clear physical interpretation needed to make this consistent. Most of the dynamics you have studied so far, you have always made an assumption that body reference coordinate system is located in the center of the mass. Okay, so let's continue. Mass moment of inertia. Same thing, so I have my vector u bar. Once I do my integration from 0 to L, 0 to H, I'm going to get this solution. Mass divided by 3. Remember in the previous case, it was mass divided by 12. So obviously, this is bigger. Nah, I wanted to put like this. Yes, sir. So you can use just a, yes. Yeah, you can use a pre-calculated table to get these values. Because, there's a different kind of handbooks about mass moment of inertia for different shapes of bodies. Use that. Don't do this.
Most of them are based on the center of mass.
Correct. But then you can use something that is called parallel axis theorem. Parallel axis theorem is well, you know what it is. So simply moving your inertia properties with respect to another location. So parallel axis theorem, I got the shortcut in my brains. Because that has a different name too, but yeah. Something like that. Okay. Let's call it parallel axis theorem. That I think it is something like that. Yeah. That I have never heard. Absolutely never heard about that. But let's call that as a parallel axis theorem. But even higher, I think in some of the pre-calculated tables, they can give you the mass moment of inertia with respect to different locations. Like beam-like body, it's a very common case. So it gives you like, okay, what if it's going to be with respect to middle or what with respect to the end? So this is the stuff you can get. If it is somewhere here like 1/4 of the length, then you need to use a parallel axis theorem. Yeah, Hydrogen-Steiner theorem. How come a simple theorem can be called that complicated way? That I don't understand. Like it's not very complicated, but when you read it, it's like, oh my God, this is like a real rocket science. But it's not really. So it's not so complicated. Okay, here comes very complicated question to you. Oh, not yet. So let me assemble these mass metrics. You see that now this is a no longer a diagonal representation because we have an off-diagonal component too. But again, the 2 by 2 matrix, submatrix is located here. This is my vector of 2 components. My mass moment of inertia is a scalar component located in a lower right corner of my mass matrix. My question is this: how much the body mass, body mass, body mass, body mass is increased, decreased from case A to case B. Okay, decreased by L divided by 12. No changes. Increased by L divided by 12. Increased by L divided by 3. Okay. Okay, is not add on. Okay, so let me take a look. This one. Let me take myself back. Oh, you don't even see this. Sorry, incorrect order. So we're gonna have a little bit of slow end of the class because we're gonna have 2 in-class quizzes. This one and another one. Another one is something that is all about dimensions again. Remember this: everybody needs 3 generalized coordinates. That's what everybody needs: 3 generalized coordinates. Okay. This is why the mass matrix always have to be 3 by 3. There's no other way. Then if it is a diagonal representation, that's only when the body reference coordinate system is located in the center of the mass. If not, then it's going to be something off diagonals, non-zero off diagonal components. That's a rule of thumb. But first thing first, and this in-class quiz. So what do you think? How much the body weight will change depending how you measure it? What corner you're going to measure it? So what if I'm going to measure my body weight by hanging from my left hand or my right hand? What's the difference? Is it going to be my length divided by 12, which is not so much? Or is it going to be my length divided by 3, or even no change? You say. Okay, all right, so okay, this is a high-risk game. I understand that this is something that I need to be very, very careful because the success rate 100% is, I don't know. It's possible. It's very, very possible. But is it going to be or not? Okay, we got 123 students. Ooh, I'm actually a little bit scared to press this button. Can we leave this for next week? Let's leave it next week. Let's skip this. Okay. Oh! What the heck? This is unfair. You shouldn't listen to me. You should think about this, what to do after this class, like what about the Lakers, or how is going to be my party on Friday? But it was a promise. Coffee on me. I just need to figure out how can I organize that. Ooh. Is it like what? This is a third time. Third time. Yes. But the first time you guys gonna get the coffee on me. So it's not gonna be 3 coffees, but 1. Here in the university cafeteria. I need to figure out how to organize that. Because it's gonna be, I need to, maybe I can get the coffee coupons or something. And online participants, I don't know how I can give the coffee for them. Thanks God, they're online participants. I don't feel that bad anymore. How you want to go? How you want to do this? You want to go and have a coffee after Last lecture, or you before the last lecture, or how you wanna or you would like me to give a handout there, these coffee coupons, or what's the way to go? Before the so after or before? Yeah, I'm gonna ask. I will ask. Okay, so the WhatsApp officer, please ask like how you would like to get your coffee served, how you want to have your coffee. Okay, so but the second one, if you guys score 100% this, still only one coffee, because you don't need to think about your stomach. Coffee is not healthy if you drink too much coffee. Uh, okay, but now when I click this, I think it's gonna yes, not the way I want. Okay, there's gonna be another in-class quiz. I just need to move to that one. Okay, the last one. But seriously, I am surprised because usually people get very, very confused about this thing that the body mass is changing. They somehow mixing the body mass to mass moment of inertia, and it's not so straightforward you think that it is. Okay, but now here's another question. Again, my rectangular shape of body, what is the mass matrix for this kind of the body? And I have three choices here, four choices, excuse me. So the first one is the one with non-zero off-diagonal components. Then is a diagonal representation. Then is mass of the body, and then it's going to be skew symmetric. This, by the way, this kind of a representation is called skew symmetric form of the mass matrix. So which one is correct? Only one is correct. Is it really? How come? Yeah, I noticed. So it's black. So what did I make incorrectly? Display. Let's look at this one. This one is doing the top. So how is an answer? How is the people would like today coffee to be served? Hold on. Is it? Yeah, I think it is okay now. Uh, So how after last lecture? So it's going to be late. You're not going to sleep well if you're going to have a coffee that late. Okay? But I think we need to have it before that because isn't it so that the cafeteria closes at 6 o'clock? Is it so? The cafeteria, the one that is located this Sky, no, what it is a street cafe. Yes. Isn't that the one that is closing at 6 o'clock? Okay. I'm actually very, very pleased to offer you a coffee because it's going so well. It really is going so well. Okay. Super happy to do so. Okay, but this one. Okay, what about this? Sometimes they say double or nothing. You want to go this way? Double or nothing. You know that's what they do in gambling all the time. So you win something, they ask you want to continue, you can get this double or nothing. Let's not go this direction. Let's skip this one, and then there's something else. The last thing that I want to explain today, I'm gonna get started right after this. Are you guys all done with this in-class quiz? You're done. Okay, so let me move on to the last subject matter today, which is quadratic velocity vector. This is going to be the last component we need. And then we're ready to set the equation of motion. So we're this close to set the equation of motion. And this quadratic velocity vector is, as the title implies, is quadratically related to velocities. And this is the component that came through this procedure we looked at earlier. So this one guy that is quadratically related to angular velocities. That's what it is. Okay, let's look at the details and let's look at what is an interpretation of that. Right, so a component look like this. So I have this particular part that I got from my concept of virtual work and when I was expressing the acceleration the way I did. And I have here angular velocity power 2, and then the component here in the middle. So once you do this math, this is how you can write it. Now, extremely important to understand this, that this particular part going to be equal to 0. And you can testify, okay, you can actually prove this by looking at the lecture notes. So there is a detailed explanation why this particular component becomes to be 0. But this is simply because I have my rotation matrix rotated 90 degrees and its original form. So they kind of compensate each other. When they do that, this particular part, it's going to be 0, which is scalar component. What is left is going to be the component associated to Rx and Ry. Now, when you look at these components, they're kind of like a forces that you can experience when the body is rotated. So it's like this. So you have a being-like body, and you're measuring the forces that is coming from this centripetal forces. You have your body reference coordinate system located in the middle. Now, when rotating this, like how much forces you will experience. Let's say that you have, let me make this even more simplified. So you have a revolute joint here in the middle, and then you're rotating this body. So how much are the force component in your revolute joint that is trying to rip this off? No forces. It feels nothing because this is exactly in the middle. So when I rotate this bar, this is ideal. They cancel each other. So remember, this is ideal beam. Jussi Sopanen is explaining, okay, there's no such thing like ideal rotors, ideal beams. There is always a misalignment, this and that. We have ideal world. Let's have it. Let's make our world to be more simplified than Jussi Sopanen's world. Jussi is like, he want to make his life miserable. Very, very difficult. We don't care about these minor things. Let's just say approximately no forces whatsoever. But if you have a revolute joint in the end, and now you rotate it, can you feel the forces? Yes, you feel the forces. You feel that they really want to take this off. So they really want to fly. Like, of course, I can handle it, but if it want to go like this, but the forces are preventing that not to happen. This is an interpretation of quadratic velocity vector because even though that is kind of misleadingly named, it's a velocity vector. It is a force component. That's what it is. So it's considered as a force like other components in equation of motion. In equation of motion, we have nothing but forces. Nothing but forces. Okay, this force is the one that feels when you rotate it, the system in a case where the body reference coordinate system is not located in the center of the mass. That's what it is. Okay, last thing that I'm going to do today is, because the next thing is that I'm going to move on to equation of motion. Equation of motion is going to be something where we simply summarize everything we have learned so far. There's going to be interesting thing that I'm going to highlight to you, like just a peek, and then we're going to close the case today. Something that we can actually summarize all the components, and we can adding the components. So the dynamics is different than, for example, finite element method that is used in structural strength analysis. Because in structural strength, the finite element, you're kind of sharing the degrees of freedom. In dynamic analysis, we don't. We're just adding the degrees of freedom regardless how they are possibly combined by joints. We don't care about that. And we learned this already because if we have one body, we need 3 generalized coordinates. If we have 2 bodies, we need 6, regardless of the configuration, regardless of the constraints between them. If we have 3 bodies, we have to have a 9, so on and so forth. So we're always adding the number of unknowns. And that's exactly what we're going to do. We're going to use something that is completely different concept than the finite element method because we're going to use block diagonal representation of the system matrices. Block diagonal representation means that they are not sharing degrees of freedom. So there's clearly like one body, second body, third body, so on and so forth. They don't have any overlapping degrees of freedom as it is the case in the finite element modeling. Okay. That's what's going to follow next week, Monday. But let's look how we're doing in in-class quiz. Is it going to be another fourth time 100%? Let me see if I got a thumbs up. Not enough, I guess. 46. Is it a 46 thumbs up? That's an all-time record. How much money am I going to get from YouTube because of this? It's like, is it like 46,000 euros or much? Or how much? Is it less than that? Yeah, I guess it is less than that. Okay, but this is what I wanted to show you. All right, so we got 119 students. 100 by the way, it was expensive trick that I did because 100 and something students multiplied by coffee cup, so it's going to be more than 100 euros. I don't care. My wife, let's keep it this confidential information. Can we? Okay, it's between you and me. Okay. Oof. How come, this time it was again very high, but I don't understand. How come you scored so well in the last time? That I'm still confused. Still very confused. Okay, that's all for today. We're gonna continue from equation of motion on Monday, and then we're gonna start solving the dynamic responses. Dynamic responses. What's left is summary. Oh, so there've been every now and then questions about how is this midterm exam. So let me repeat. So midterm exam is going to be organized in Moodle. You can use any material you want. Highly recommended that once you're solving your weekly assignments, please keep those assignments and solutions somewhere in your folders because they becomes to be handy because there are similar kind of questions in midterm exam. You're going to have a 1 week time to make 2 attempts. You can do that anytime you want during this 1 week time. And the highest will be accounted. That's how we're going to go. I have more instructions available, not next week, but week after that. Like how exactly in details you can do this in this midterm exam. Remember, it's not going to be everything you need in this class because it's only 30-something percentage of the maximum points, but it's a good part of good percentage of the maximum points. Okay, guys, take it easy. And how we're gonna take coffee again is gonna be in the last lecture before the lecture. Before the last lecture, and the last lecture is gonna be, is it all as late as December, isn't it? So it's gonna be late. Anyways. All right. I wanna congratulate you for winning this coffee cup. Good job. And see you guys Monday. Okay, let me close this streaming.